Alright, so in this video I'm going to be explaining another important article with the title Deep Graph Representation Learning and Optimization for Influence Maximization. This ICML paper in 2023. Influence maximization is formulated as selecting a set of initial users from a social network to maximize the expected number of influenced users. Researchers have made great progress in designing various traditional methods, and their theoretical design and performance gain are close to a limit. In the past few years, learning-based influence maximization methods have emerged to achieve stronger generalization ability to unknown graphs rather than traditional ones. However, the development of learning-based IM methods is still limited by fundamental obstacles, including the difficulty of effectively solving the objective function, the difficulty of characterizing the diversified underlying diffusion patterns, and the difficulty of adapting the solution under various node centrality constraint IM variants. To cope with the above challenges, we designed a novel framework, Deep IM, to generatively characterize the latent representation of seed net sets, and we propose to learn the diversified information diffusion pattern in a data-driven and end-to-end manner. Finally, we designed a novel objective function to infer optimal seed sets under a flexible node centrality-based budget constraints. Current efforts on learning-based influence maximization method solutions are still in the infancy stage due to fundamental obstacles such as the difficulty of efficiently optimizing the objective function. Also, the difficulty of automatically identifying and modeling the actual diffusion process. Also, the difficulty of adapting solutions to various node centrality constraints influence maximization problems. And these are the related works: learning-based influence maximization, and then some people use reinforcement learning. Also, graph neural networks. So what is the problem? The generic influence maximization problem requires selecting k users from V, from vertex set, as a seed set. So these are influence nodes. They affect many nodes. So we want to maximize the influence spread, this one. Now, the evaluation of influence maximization relies on an influence diffusion model parameterized by theta. So we are parameterizing this model with theta, and theta can be the set of infection probability on each node if M is an independent cascade model, or the set of parameters in the aggregation or combined function if M is GNN based. So assume that M is just a GNN network with parameter theta. So we propose Deep IM to ease the computational overhead of learning-based IM methods and automatically identify the underlying diffusion patterns. The framework can be divided into two phases. The learning phase is leveraged to characterize the probability of the observed seed set and model the underlying information propagation distribution, and the inference phase. So we have learning phase and the inference phase, where inference phase is employed to optimize the selection of seeds in continuous space to maximize the influence spread. So instead of directly modeling the highly interactable probability P of x, we introduce an unobserved latent variable z. This z, which is unobserved, we condition on that, to represent x and define a conditional distribution to quantify the likelihood. These latent variables have much lower dimensions than the observed suboptimal seed sets, which can yield a compressed representation. Particularly, we marginalize over the latent variables to obtain P. This deep IM consists of two parts. We leveraged autoencoder to learn and compress the latent distribution of seed node sets into lower dimension. The lower dimensional P of z is then leveraged to learn an end-to-end and monotonic diffusion model for accurately predicting the spread. In addition, we employ a knowledge distillation module to train a lightweight student model to retain efficiency in predicting the influence spread. The seed set inference scheme iteratively optimizes the proposed objective function by updating the latent variable z, initially sampled from the learned P to maximize the influence spread. And then we have a knowledge distillation here. That is a learning part. So this is this inference part. Once we have learned the latent distribution of seed nodes, the next step is to update the seed node set in order to increase the marginal gain of influence spread. So we design a GNN-based model diffusion M for accurate modeling of the relationship between X and Y with considering the overall graph topology. The output of a GNN-based diffusion function is composed of two functions. Tau, where G is GNN-based aggregation function, and tau is just a vector of 0 and 1, continuous vector of 0 between 0 and 1. Tau denotes the infection probability of each node. That's why the size of the vector is the cardinality of your number of vertices. And so Y denotes the final information spread, where G is a normalization function, and C is the threshold to transform the probability into discrete values. So M is score monotonic, and these are definition of score monotonicity and infection monotonicity, because it's a natural property for us in modeling the overall diffusion network structure. A monotonic diffusion model indicates the spread of influence would continue to increase. Intuitively, if we select a larger community X prime as a seed set, the larger X prime would intrinsically infect no less nodes in the whole network than a smaller seed set X, if this relation holds. So ensuring the property of both monotonicities allows us to better characterize the underlying diffusion network structure and mimic the real-world diffusion pattern. So we add constraints to make GNN-based diffusion model monotonic during influence spread estimation. So due to space limitations, we use knowledge distillation for diffusion estimation efficiency. We have learned the deep representation of seed nodes and an end-to-end diffusion model with a monotonicity. However, we empirically find the calculation of influence spread involves 3 steps. First, decoding a node vector X from Lerner posterior. And second, executing the GNN-based diffusion model under the graph. And third, normalizing the probabilistic output from M to actual influence spread. Even though the prediction results are accurate, the computational overhead is still a burden when dealing with million-scale network. Inspired by recent research on knowledge distillation, we propose to leverage a small yet powerful student model supervised by M. So this is how we do end-to-end learning. And we use negative log likelihood here in equation 5 and derive its lower bound. So we use the Jensen inequality. Now we can have a lower bound, and the overall objective consists of just minimizing this empirical error. So now we want to infer the inference time. At the inference time, to infer the high influential seed node set in the testing domain, we leverage the latent distribution P of the seed node set and the end-to-end diffusion model jointly from equation 6. So if autoencoder is well trained and can retain both continuity and completeness, the autoencoder can generate contents by exploiting the latent feature space. So we propose to alternatively search the optimal seed node set in the lower dimensional and less noisy latent space, which is probability of Z. Since introduction of influence maximization in 2003, it was studied under various budget constraint setting on nodes in recent years. To enhance the adaptivity of DeepIM, we design a unified constraint that allows inferring seed sets under various budgets on individual nodes. And this part is a generalized budget constraint applied on individual nodes. And K is the actual budget. So this is the algorithm. Once we have given number of training instances, number of iterations, we create the seed set, then we regularize, we update the Z. Z is our latent variable. Once we get Z, we can have phi. We can have X tilde. So this is the interesting visualization of influence spread in JAS dataset. The size of nodes is determined by the node degree, and the color of nodes determines the infection status. Blue means the node is in seed set. Red means the node is infected. And gray means the node is not infected. So we have different data sets like JAS, synthetic, and different methods, but the paper is DeepIM. So comparing with different methods, you can see under SIS diffusion pattern, you can compare. Also, this figure is the visualization of influence spread in JAS dataset.